In this video, we'll be looking at how to take the derivative of an exponential function. And we're going to start off by using the first principles of derivatives to try to find the derivative of f at x equals b to the power of x, where b is any base. So f prime of x is going to equal the limit as h approaches 0 of f at x plus h. So b to the power of x plus h, subtract f at x, so b to the x, all over h. Similar to how we did this for the exponential function when the base was specifically the natural number e, we're going to do the same idea where we're going to factor out b to the power of x because both terms have it in common. When I factor it out from the first term, we're left with b to the power of h. When I factor it out from the second term, we're just left with 1. Okay, now b to the power of x is not going to be affected by the limit as h approaches 0 because it does not contain h in it. So I'm just going to pull it out of the limit. And we'll have the limit as h approaches 0 of b to the power of h, subtract 1. All over h. Now again, unfortunately we cannot use a factoring method or a conjugate or change of variable, any of those strategies we've seen in the past with limits. So I am just going to do a little bit of a test value. So I'm going to, for each of these cases, I'm going to set h equal to 0.0001, and I'm just going to see as my base changes to different numbers, what is this limit approaching as h approaches 0. So let's say my base was 2, and I was finding the derivative of 2 to the power of x. Okay, let's see what the limit as h approaches 0 of 2 to the h subtract 1 all over h will be. So I'm just going to replace h with 0.0001, punch it into my calculator and see what I get. And I get approximately 0.69. Okay, that doesn't really mean anything to me. I'm going to try my base being 3. So for this one, I'm going to take the limit as h approaches 0 of 3 to the h subtract 1 all over h. And again, I'm going to sub in 0.0001, punch it into my calculator, and I get, approximately 1.10. Again, this doesn't really mean anything. We did try this when we had Euler's number. So if my base was e, let's just refresh on what happened to the limit as h approaches 0 of e to the h minus 1 all over h. And again, if we sub in 0.0001, we actually get just 1. So when it was the natural number, we got a nice number. When the base was something else, 2, 3, if I tried other values, again, I don't get numbers that mean much to me. So let's see if we can think about why we got 1 or what expression is equal to 1. Well, we know that ln of e is equal to 1 because ln is the natural logarithm where the base of the log is e. So it's like log base e of e, that's equal to 1. Let's see if ln of 2 or ln of 3 is equal to the values that we got. So if you punch in ln 2 into your calculator, you do in fact get 0.69. If you type in ln of 3, again, you get approximately 1.1. So it looks like the limit as h approaches 0 of the base to the power of h subtract 1 all over h is equivalent to ln of the base. So this portion here, I'm going to keep b to the power of x, and that will clean up to ln b. So let's put that together. If f at x is equal to b to the power of x, the derivative is b to the power of x times ln b. And ln b is just a coefficient. So if you would prefer, you could write ln b times b to the power of x. Either way. Specifically for e to the power of x, we already know that the derivative of e to the power of x is itself, but here's the proof of it. Using our new definition for the derivative exponential function, it'd be the base to the power of x, so e to the power of x, times ln e. But ln e is 1. And that's why the derivative of e to the x is itself. It does follow this new definition, but because ln e is equal to 1, we just see it as the original function. Now, going back to b to the power of x, what if we have a function within a function? So b to the power of something else, we have to use the chain rule. And the chain rule says, take the derivative of the outside function. So it's going to be b to the power of the function times ln b. So that's the outside derivative. And then multiply that by the derivative of the inside, which in this case is the derivative of the exponent. And here we are. And those three pieces are all attached by multiplication. So now let's try actually taking some derivatives. So if I have y equals 2 to the power of x, y prime is going to be, I'm just going to put the ln out in front. So ln 2 times 2 to the power of x. For the next one, 3 times 2 to the power of x. The coefficient of 3 doesn't affect anything really, so it's just going to be 3 times the derivative that we already found. Y equals 3 to the power of x. Y prime is going to be ln of the base times 3 to the power of x. And the derivative of 1 is 0, so I'm not going to write that. And now let's go into fancier derivatives where we'll use the chain rule, maybe we'll see a product rule, a quotient rule, previous derivatives. So let's take a look. We have e to the power of 2x plus 1. So a prime of x, I don't have to write ln e because I know that's equal to 1. So I'm just going to write e to the power of 2x plus 1. There's the derivative of the outside function, and that'll get multiplied by the derivative of the exponent, which is 2. And I'll just write that 2 out in front because it looks a little nicer. For the next one, we have a product rule because we're multiplying x squared with 3 to the x. And we get the derivative of the first function is 2x, and that'll get multiplied by 3 to the power of x, plus the derivative of the second function is ln of the base, so ln 3, times 3 to the power of x, and then that will get multiplied by the original first function. And there we are. For the next one, 4 to the power of 2x, we have a little chain rule here. So c prime of x is going to be, first we're dealing with the outside function, which is that we have 4 to the power of something. So ln of the base, so ln 4, times 4 to the power of whatever it is. And now to acknowledge that inside function, I'm going to multiply by the derivative of that exponent, which is 2. And just to clean up, I'm going to put the 2 and the ln 4 together. So that's like the coefficient, and then times 4 to the power of 2x. Next, we have 3 to the power of sine x, so another chain rule, but now bringing back our trig derivatives. D prime of x is going to be, we're going to start with the outside function, so 3 to the power of something, so ln 3 times 3 to the power of whatever the exponent is, and now time to take the derivative of the exponent, and the derivative of sine is cos. All right, let's continue. We're going to get a little bit more interesting. 2x times e to the power of 3x. So we have a product rule because we're multiplying 2x by e to the power of 3x, and we have a chain rule because we have e to the power of another function. So let's start with our product rule. The derivative of the first function is just 2. Copy paste the second function, plus the derivative of the second function. We're going to take ln base e, but that's 1. So I'm not going to write it. Just going to copy paste e to the power of 3x. Now I'm going to take the derivative of the inside function, which is 3, and now copy paste the first function. Just going to clean up this part here. 2 times e to the power of 3x plus 6x times e to the power of 3x. If I did have to do something with a question like this, I would factor out e to the power of 3x, and then I'd be able to set my derivative equal to 0 and solve. All right. Next one, 4 to the power of cos of x squared. So we do have a double chain rule here. Our outside function is 4 to the power of something. Then the inside function is cos of x squared. But the inside function has its own inside function, which is x squared. So we have to be very careful here and not lose track of what we're doing. So first thing, I'm going to take the derivative of the outside function, which is 4 to the power of something. So ln 4 times 4 to the power of whatever we have. Okay, there's the outside. Now I'm going to go to my first inside function, which is I'm taking the derivative of cos of something. The derivative of cos is negative sine of whatever it is you're taking. So here it is. There's me taking the derivative of the outside function of the exponent. But now I also have to take the derivative of the inside, which is 2x. And if I were to clean up anything here, I might just put the coefficients together, like bring the 2x out front, put the negative out front. So maybe negative 2x times ln 4, or negative 2 ln 4 to really be the coefficient, times x, and then everything else. There's different variations. And there we are. For the next one, again, we have a few chain rules in here, but now my outside function is going to be cos. And feel free to pause this video, try it for yourself, and then check back. All right, the derivative of cos is negative sine, and I'm going to copy paste its inside function. Now I'm going to take the derivative of its inside function, but this one has its own chain rule, so I'm going to start with the outside function, which is ln 3 times 3 to the power of 4x squared. And now finally, time to do the most inside function to get 8x. If I wanted to clean up, maybe I put the 8 out front, the x, the ln 3 all together, then sine of 3 to the 4x squared, and then 3 to the 4x squared. All right, final one, we have a product rule here. E to the 4x, so its derivative is going to be ln e, which is 1, times e to the 4x, and then the derivative of 4x is 4, just going to put it out front, times the second function, plus the derivative of sine is cos, and then I'll copy paste e to the 4x. Just going to write e to the 4x first. Just personal preference. And there we are. All right. Next we have one word problem and then a final little optimization question. So a bacteria colony is growing inside a petri dish. At noon, the population was 124 bacteria, and it has been doubling every 8 hours. Determine the bacterial population at noon the next day. So first thing, we need to create a function to represent this growth. So I'm going to use P for population and H for hours. And now we have P at H equals the initial population, which was 124 bacteria, our rate, which is doubling, so 2, and it doubles every 8 hours, so that's H over 8, which can also be written as 1 over 8 times H. All right, now we're ready to find part A. The bacteria population at noon the next day. And this scenario is starting at noon the current day. So that's just 24 hours later. So we need to calculate P at 24, which is going to be 124 times 2 to the power of 24 over 8. And if we punch this into our calculator, we get 992. So therefore, the population will be 992 bacteria. All right, what is the instantaneous rate of change at noon the next day? So now we're talking about the derivative, the rate of change. So I'm going to find the derivative, the 124, because it doesn't have a variable attached to it. It doesn't affect the derivative, so I'll just write it. The derivative of 2 to the power of something is ln 2, and then we'll multiply that by 2 to the power of whatever our exponent is. And now time to take the derivative of the exponent, which is just 1 over 8. Now I'm just going to clean this up. 124 times 1 over 8 is 15.5. The ln 2 stays. And then 2 to the power of h over 8. And now we're ready to sub in 24. And we get approximately 86 bacteria per hour at noon specifically. All right. Final example. Determine the absolute maximum and minimum values of f at x equals x squared times e to the x, given the interval x is between -4 and 2. So max and mins occur when our derivative is equal to 0. So step 1 is going to be the derivative. And we have a nice product rule here. So the derivative of x squared is 2x times e to the x plus the derivative of e to the x is itself, and then that'll multiply by x squared. Now I'm going to set my derivative equal to 0, and because I need to solve this, I am going to factor out an e to the power of x and an x, because they have that in common. When I factor it out from the first term, we're just left with 2, and when I factor it out from the second term, I'm left with x, when I divide out that GCF. And now I can branch out. X equals 0, e to the x equals 0 has no solution. And finally, 2 plus x equals 0, so x is -2. Both of these critical points belong to this interval that we were given, so I will include them in my testing. I'm going to test -4, I'm going to test -2, the 0, and the other endpoint. And now, just going to punch it into the calculator. So -4 to the power of 2 times e to the power of -4. And we get approximately 0.29. I'll do the same thing for -2. -2 squared times e to the -2. Approximately 0.54. So far, that would be winning as my max. F at 0 is just 0, because 0 squared is 0. And for 2, 2 squared times e to the power of 2 is 29.56. So when I look at this, 2, 29.56 is our absolute max, and 0, 0 is our absolute minimum. And there we are. We went over the derivative of generic exponential functions, tied it into the chain rule, added in product and quotient rule. We did a little exponential application and a little bit of max and mins with critical points.